Can I just switch in for a minute? Don't need this. Okay. So we are planning to go to Mahabalipuram this Sunday. So those who are interested, please. Prerna. So, no, we need to know the head count. So we need to, can you send me, maybe you can send me send Pratik an email that you are willing to come, right? Yeah. Okay, I think the Prerna is good. Yeah. So, yeah. Okay. Oh, that's true. Oh, okay. Okay. Neil. So please contact me to be count by tomorrow. At least you need, right? Yeah, by tomorrow you should know, right? Because all. You know, yeah. Anyway, just write an email if you're planning to come. Okay, that will be.
Okay, so let's get started. So from what Manjari told me, this is also a general purpose seminar, although it's part of the conference. So this is a more general talk for the rest of the audience. So, so it's a great pleasure to introduce Maura McLaughlin, who'll talk about the pulsar timing array C-RED entering the era of low frequency gravitation wave detection. So Maura has been visiting India for about 2 weeks or something, and she gave I know she gave a lecture at ICTS, and there Ajit gave an introduction for about 15 minutes. Unfortunately, I'm not prepared any such thing, but let me just say in one sentence that Maura is really top of the food chain on nanohertz gravitational wave astronomy, pulsar timing, and more or less anything and everything associated with pulsar. So that is
a little bit offended because it's really vegetarian, so I think it'd be food chain. So build on everyone talking about possible date. To me, people who don't know about what a pulsar is or what gravitational waves are. So I'm going to go through like my introductory slides pretty quickly, I think. But let me just start first by talking about the collaborations that this work is a part of. So I'm a member of NanoGrav. Most of you have heard of NanoGrav before, but this stands for the North American Nanohertz Observatory for Gravitational Waves. So we're a collaboration made up of folks in the United States and Canada. We use North American telescopes. There's about 150 of us, something like that. Many of them students. We have a really large number of graduate and undergraduate students at about 50 institutions. We're funded by the National Science Foundation. We're a physics frontier center. That's really awesome. I think the situation here in India with funding is different, but in the US, it's really a pain to get funding. You have to apply for grants every couple of years. You might fund one student. This PFC allows us to have a really joint institutions for our students. PFCs people. And of course, NanoGrav is a member of the International Pulsar Timing Array, which is part of why we are all here. So the IPTA is a consortium of consortia. So it includes NanoGrav and then other pulsar timing array collaborations in Europe, Australia, and now India. And so last I counted, there were 11 countries, people from 11 countries in the IPTA. I think we have something like 300 participants, something like that. So that's sort of an idea of the scale. Our last meeting was actually here in India. I was mentioning to someone that the last international trip I took before this one was also to India. So when I go big. And yeah, so this was a great meeting that was hosted at NCRA in Pune back in June 2019. The meeting this summer, we'll have our first, again, in-person meeting this coming summer, which is really exciting, and that'll be in Australia. And if you're a student, you probably have associated with these meetings. They're really great. You know, feel like ways to comment about what's happening actually. But just a little bit of background. We've seen this before. We've heard a lot of possibilities about micro-conditions. This stellar grade sort of shows the black hole are neutron star binaries that have been detected by LIGO. I think everyone in this audience is familiar with LIGO, black holes, gravitational waves, so we're going to skip that part of the introduction. But you can see that the mass range that LIGO is sensitive to, let me see if this works. It's kind of faint, but you can kind of see it, is of course something like, 2 solar masses up until a couple hundred solar masses, right? So these are the masses of the compact objects that ground-based interferometers are sensitive to. Before we start talking about like the pulsar timing array and the detections that pulsar timing arrays are going to make, let's just think for a moment about how much we've learned in the past, 7 years from LIGO, right? So there have been some very expected insights we've gleaned, right? Like masses of black holes. And we've also learned a lot of things, general relativity, new information, and there's probably going to be all of these guys and others. And we're trying to see before we start to talk about pulsar rates for this cartoon, it works. I think it's kind of a nice analogy, and it's why we expect to see relations we do. So what this vision shows are the 2 lasers, well, the one light source laser that's split along 2 arms. And these arms are in an L shape, right? And so in LIGO, these lasers travel along these arms, which are at right angles to each other. They bounce against mirrors. They go back and forth. And if a gravitational wave passes, I think we just missed that in the cartoon, but hopefully you saw it. When the gravitational wave passed, one of the arms was stretched a little bit longer and one of them was squeezed a little bit shorter, right? So when gravitational waves pass through objects, they stretch and squeeze them, and they do them in this quadrupolar way, right? Which is why the LIGO arms are at 90 degrees and not at 0 degrees or 180 degrees, right? So one arm gets a little bit longer, one arm gets a little bit shorter, and that difference in path length is picked up here in this interference pattern, right? So this is how ground-based interferometers work. So LIGO detects so stellar mass objects. Is much more holes. Our timing rate, we need to build much deeper gravitational wave. So the goal of pulsar timing rates to build scale gravitational waves lasers, we use natural pulsars, which they the pulsars. This is a, oh no, my screen has gone. Hopefully it'll come back. There we go. Yeah, so this is a, let's see if I just need to wiggle it. Yeah, okay. So this is a nice little cartoon showing the concept of a pulsar timing array. So here we are on the Earth. A PTA is just what it sounds like. We observe an array of pulsars distributed across the sky. Each pulsar is at a different distance. Each has a different spin period or different spacing between pulses. Each has a characteristic pulse shape. And the important part of this timing array is that in order to detect gravitational waves, we need to observe more than one pulsar and analyze the data all together in a correlated way, right? So pulsar timing array is used to search for correlated perturbations and pulse arrival times across an array of objects. So pulsar perturbations, and notice that line goes. So when the gravitational wave passes, right, it for stretch arms gravitational waves, figure out the entire series. We make gravitational waves means due to gravitational waves and data, it has two terms. There's a pulsar term that tells us what the gravitational wave perturbation was when a radio pulse left the pulsar. And there's an Earth term, which tells us what the gravitational wave perturbation is when that pulse hits the Earth and we detect it, right? So we have this pulsar term and this Earth term, which is a little bit different than the LIGO experiment. Otherwise, this is really much the same, right? We're looking for very small changes in light travel time between 2 points. It's the same idea as LIGO. And of course, we want to search for very specific angular correlations in arrival times due to gravitational waves. We can't detect them in just one object. We need to search for this correlated signature across all the planets. Separation between the pulsars, right? It really just depends on the separation between the pulsars. So two pulsars in the same direction, that way, or that way, are all going to have the same, level of correlated times of arrival. Okay. I think is that this kind of right. Because waves are hitting them at different times. This correlation further up. Detecting the influence of the gravitational waves on the Earth itself, right? Not the pulsars. Okay. This is what we want to look for in our data. So let's talk about how we build a galactic scale detector. And again, the next few slides are going to be review for those of you who've been here for the past couple of days. So we're going to use pulsars. We're going to use a special kind of pulsar called millisecond pulsars. So these are pulsars that have been recycled to very short periods through accretion of matter and angular momentum from a companion star. We know of over 3,000 pulsars now, and over 500 of them are millisecond pulsars. This is actually really dramatic. Just like, I don't know, 5 years ago, we were at maybe a couple hundred. We found a ton of millisecond pulsars, maybe 300, but a lot of millisecond pulsars over the past couple of years. Many of the new ones are discovered with FAST, the huge telescope in China. So we have a large sample of pulsars that we can time for a PTA series. So we are sensitive to very low frequency. So one thing that is, I think data for very long time spans. So Nanograv is currently releasing its 15-year data set. The IPTA has almost 30 years of data on some pulsars. And so unlike LIGO, which can only detect very short time scale gravitational wave events, right? So things like seconds to maybe 50 seconds for that double neutron star signal that we saw that just went like on and on and on. Pulsar timing arrays are able to detect signatures. I don't know why this keeps happening. Yeah, are able to detect signatures that are very long time frame. I think it's my laptop because I've not had this issue before. Anyway, well, I don't know what's going on. I'll keep talking while we're trying to fix it. Like, sometimes, yeah, very long times data, right? And there's very long times of data out a very long period, very low very special. It's extremely long period. Oh, there it's back. Oh, maybe not. This looks like it was. There we go. Briefly. Yeah, I don't know what's going on. Anyway, I could join the Zoom and then just play it, you know, on the Zoom, and then I wouldn't need to depend on this, right? What's that? I think it's over.
Yeah, that would be a good suggestion. I think. Yeah.
But it's not, my screen's not sleeping, actually. It's just like the connection, I think. Oh, what happened now? Sorry, everybody. I don't know what's going on.
Yeah, that would be a good suggestion.
But my God is now like frozen. I've been fine though. I don't know what's going on. It's really weird. Yeah, this is really weird. Sorry. Should I shut down? Go back? Yeah, sorry, everybody. Yeah, it's not super low on power, so I don't think that's it. Yeah, sorry. We'll be back.
Now rebooting.
Yeah, it's rebooting. Are there any questions so far? Because it's going to take a minute. Oh, no, now it's back. Here we go. Okay.
We didn't connect that way, red color showing. We want.
Okay, it is back. I don't think it's my fault, but maybe I should turn off the sleep setting. Okay, you know, just in case there's some issue. Let me just get rid of all this stuff. Yes. I need to see something. Instead of turn off. Yeah.
Just connected.
Sorry, it's going through all this like weird stuff that it does when it opens up. Okay. That's not what I want. Okay. Let me do the mirroring and then we should be good, I think.
Display.
Yeah, thank you.
Is this connected, not connected?
I don't think that's.
Mirror also connected. Just I connect.
Okay, it needs to be connected to do it, I guess. Anyway. Okay,
Okay, fine.
well, it's fine for now. Um, yeah, it's not like I don't stop it looks fine. And then I don't know what's happening. Sorry. Yeah, okay. Let's put it on Google Drive and then I can download on Google Drive on yours.
It's not about only the 1 minute. Madam. Have you tried with a different port?
Yeah, we tried one more. I don't know what's going, I mean, the laptop I think is fine.
Yeah, that's
Like,
fine.
so I don't know that this is going to fix it, but
One more time.
yeah. Hold on.
1 minute.
What is going on? We set up ages before and it was fine the whole time we were just sitting here. Okay. I was going to upload it to Google Drive, but maybe that's not necessary. It's fine. It can sit there in the background, I guess. Okay. Let's see if we can do it again. Let's not worry about the power because maybe that's part of the problem. Okay. Let's all cross our fingers. Sorry. Yeah. So so the nice thing about our experiments is we're analyzing data for really long time spans, so we can detect very low frequency or long period gravitational waves. And a nice way to think about what strain sensitivity we can expect is that if you take like the average sort of precision, sort of the two of our pulsars, for the time span of the experiment, you guys can remember to get to the list. Slowly, you'll see later on that's just how additional waves we think you're seeing in our data. So we're over here in the gravitational waves here. Lisa will kind of fill the gap in between. These are two projected sensitivity curves for nanograv a few years ago and by 2030. And you can see that with time, our best sensitivity, our peak sensitivity marches leftward, right? So as we analyze longer and longer time spans of data, we get sensitive to lower and lower frequencies because this peak sensitivity here will be 1 over the time span of our data. So we get sensitive, more sensitive to the gravitational wave background as we, continue the experiment, because the background is also expected to get brighter at low frequencies, right? So it's kind of two benefits to extending the experiment. We get more sensitive ourselves and we get sensitive to those lower frequencies. As you can see in this plot here, there are two different kinds of gravitational wave sources we can detect. We can detect gravitational waves from individual black hole binaries, just like LIGO. except ours are going to be super massive over periods of years instead of actual merger events. So the summation of all the gravitational waves in the universe, all the supermassive rays in the universe, right? These types of still not those kind of searches, most recent results in this talk. Why do we want to do this? Why do we see supermassive black hole binaries? Well, there's lots of really interesting astrophysics, right? So if we look back at the galaxies that were formed in the early stages of the universe, those galaxies are really small. They're very irregularly shaped. If we looked at galaxies formed more recently, they're much larger and they're more regularly shaped, right? And we think that this process of galaxy evolution through cosmic time has happened through what we call hierarchical galaxy formation, which means galaxies have merged with other galaxies to form bigger and bigger and bigger galaxies, right? So we think that galaxy mergers are a really important part of how our universe has evolved since the Big Bang. But there's lots of things we don't understand about this process of galaxy merging. And in particular, there's a thing called the last parsec problem or the final parsec problem, which is how do these black holes at the core, this merged galaxy, right? So merged galaxy, this work. Here we can study them organically, we can see they're merging. These illustrations with galaxy, we look at it like it would just look like a single galaxy. They actually merge into one single black hole. The issue is, these will need to get close enough to replicate, bring them together. How do they get close? How many of them stall and never form one supermassive black hole at the core? So this is the whole thing that we're trying to explore with this gravitational wave detection experiment, right? We want to answer questions that are really fundamental to how galaxies have grown over cosmic time. So I'm going to describe NanoGrav and the IPTA's observing program now, like a little bit about the data and the analysis, and then talk about the gravitational wave results, and then like what's next. So NanoGrav is currently observing about 70 pulsars. We observe over a wide range of radio frequencies from 400 megahertz up to about 3 gigahertz. Those of you who were there for the last talk, for Golem's talk, you know that this is really important because of dispersion and scattering in the interstellar medium. I'm not going to talk much about that because he did a really nice job explaining that. The two main telescopes that we've used for nearly all of our data sets are the Arecibo Observatory in Puerto Rico and the Green Bank Telescope in West Virginia. So the upcoming 15-year data set that we're going to release very soon is composed entirely of Arecibo and Green Bank data. A little bit of regular data. The last one is just Arecibo and Green Bank. So we did a very small program with a very large array. This is with Arecibo. We lost access to it in August 2020, which was really sad. We added the CHIME telescope in British Columbia, so we're now getting data with CHIME. This is at low frequencies, 400 to 800 megahertz. And we have a very small program with the FAST telescope in China. The very faintest pulsars that we observe with Arecibo, we can't time them with the Green Bank telescope. It's just not big enough. We weren't able to even detect some of these pulsars with the GBT. So those very faint pulsars we're observing with the FAST telescope in China. We have, I think, 6 of them in the current program. So that's just a small program. And by the way, our 15-year data set that we're releasing very soon, we cut that data set off the day that we lost access to Arecibo. So that was like a very clean break in the 15-year data set. We decided to just cut it off when Arecibo was no longer usable anymore, which is actually a few months before it completely collapsed. Okay, this is really important. Like, even though we're adding CHIME data, we have this small ELA, we really data loss of the Arecibo telescope. We observe a lot of pulsars from once a day, CHIME to like once a great telescope. The IPTA observing program is similar, so similar radio frequencies, similar cadences. I don't have time to go into the different qualities of all the telescopes, but the gray boxes here should tell us that we're in the last IPTA data release. The ones in orange show telescopes that will be in future IPTA data releases. We created this slide when we were very optimistic that fast data was going to be added. So we have it there in orange, but that's kind of a question mark. That's the one telescope that we're not real sure if it's going to make it into future data releases as of yet. So you can see that over the past few years, there's been a huge expansion in the IPTA with 2 new telescopes in North America, 1 new one in Europe, telescopes in South Africa, of course, India, the GMRT, and maybe in the future, China being added to this global effort. So this is really exciting. And Golem already talked a lot about this, but just in case there's anyone in the room who wasn't at that talk, pulsar timing, we're going to talk throughout the rest of this talk about pulsar timing residuals. So let's just explain like usually what the stars like. We observe the star, and we can't time pulsars by their single pulses, right? So we're used to seeing the standard cartoon pulsar swooshing by. I remember as an undergraduate thinking like, enter time for each of those bumps. We did that for a few pulsars. Most pulsars need to add up many pulses over the course of say like 20 to 30 minutes. The time series just looks like noise, right, with a periodic signal underneath all that noise. So we do what we fold the data. We add up all the pulses using a timing model that has a very accurate period predicted for that day. And then we measure a time of arrival for one particular epoch, right? And that we call that a TOA. Then we have a model, a timing model, which accounts for all the astrophysics that's happening, that's affecting the arrival times for a pulsar, right? We'll talk more about these in a little bit, but I'll have stuff like the period derivative, how fast the period is changing, the pulsar's position, how it's moving in the sky, all that stuff. And we'll use our timing model to predict when a pulse is going to arrive at the next time we observe that same pulsar, right? So like a month later, we'll observe the same pulsar, we measure a time of arrival, we compare that to the model time of arrival, we subtract the two, we get the residual, right? And so these residuals are what we're going to search for gravitational waves in. You can download all our network data. You need to get a list of arrival times, like this. These are arrival times, not billion days, radio frequencies. This is narrowband timing scale. T is narrowband time scale. They're microseconds for using units for times and years. Profiles. This is a really bright pulsar, 1937 plus 21, but you can see the quality of the profiles, and of course you'll get parameter files like this one for pulsar 1713 plus 07. And it still amazes me, right, after all these years in this business of like the precision with which we can measure these parameters, right? So the frequency of 1713 on this particular epoch is 218.8118404171579 hertz, which is like pretty impressive, right? All the way down to that last significant digit. And so most of the pulsars, because this recycling process is necessary to get them to these millisecond periods, most of them has companions. This 1713 pulsar has a companion in a 67-day orbit with a ridiculously low eccentricity. Anyway, so we have parameters, medium, dispersion measure, extension information, proper motions. This is actually an IPTA So let's talk about these has coming up and IPTA. So Nanograph and the International Pulsar primary work is that like here we put out a new release of data, right? A bunch of pulsars, bunch of TOAs, parameter files. Our last data set, the one that I'll talk about the results for and that you've heard a bit about, right, with this common noise process, had 47 pulsars. Our upcoming data set will have 67 pulsars. This little schematic here just shows like how our data sets have grown with time. So our first data set was a 5-year data set that had 17 pulsars in it. Our 9-year data set had 37, our 11-year had 45, 12.5, 47, and now our 15-year data set, we're looking at 67. I think it's actually 68 pulsars now. And these are the pulsar names on this y-axis. So pulsar searches have been a really important part of our program, right, to continue to add pulsars to this array. The different colors are different radio frequencies. So that's why you see these different colors there. Okay. IPTA also puts out data releases, not as frequently. For those of you who do IPTA work, you know this is because it's very complicated combined data, all these different systems. Last IPTA data release, there were 65 millisecond pulsars in that release. This time since it's longer than the rest, about 30 years, most of these pulsars, similar frequency range, a similar spot, all pulsars observed here, and the colors are different PKs. So you can see there are some very, very long data sets going way back. This is like 30 years ago. So this is a very complementary data set to the data set of any individual PTA. So compared to Nanograv, this has a much longer time span, different frequency coverage, and there's some pulsars that are observed by more than one pulsar timing array, which is a really nice kind of like double check on the data. And all of this is publicly available as well. So we search for gravitational waves by cross-correlating pulsar timing residuals. You saw examples of residuals in Golan's talk. I won't spend too much time talking about residuals, but this is just like 3 kind of random pulsars that I pulled out just to show an example of what these look like. So these are from Nanograv's 12.5-year release. So there are 12.5 years of data here. This scale is in microseconds. You can see in general, these residuals are all well less than microsecond. That is doing a great job modeling all the astrophysics that's happening with these stars. Well, the outliers, you can see the same thing here, right? We certainly have some kind of arrival that are outliers that have our zero. These aren't big problems for the gravitational wave analysis, but we're only looking for the cross-correlated features. But there are these things don't understand. Okay. We still try really hard to understand all of them though, right? Some of them may be due to mismodeled like ISM effects, RFI, things like that. And we do run all these through a basic outlier removal process before even getting to this stage. These are the things that kind of made it through that we don't understand fully. A couple other things you'll notice is we've increased the cadence of our observations quite a lot, right? The points are like much more finely spaced here than they are here. That's due to getting funding that's let us, buy time on our telescopes so we can get more time. And if you're curious about these lines here, these dotted lines, these are when we upgraded the instrumentation. We went to wider bandwidths. So the error bars generally get like a little bit smaller past these lines. This one has 2 lines because we observe it with both Arecibo and Green Bank. And then that's why it has more colors as well. This is 1713, by the way. Okay. Yeah, and so the way we quantify like how good a timer a pulsar is by the root mean square of the residuals. For our 12.5-year data set, they range from about 16 nanoseconds to about a microsecond, a little more than a microsecond. And that's sort of the level of timing that we're looking for pulsars to actually contribute significantly to gravitational wave detection work. IPTA pulsars have residuals too. This is just like kind of eye candy. I don't have time to really go through all of these plots, but you can see an example of the residuals for some of the IPTA pulsars. These range from about 0.2 to 10 microseconds. These are a little bit higher than the Nanograv data set. The IPTA data set is older. It's not as up to date as the Nanograv one because it just takes so long to put these together. And also some systematics come in when you combine all the data from these different telescopes. So you can see lots of different signatures here, right? So some of these residuals look what we would call, like they look white, right? So they just look like non-time correlated noise. Some of them we see quite red noise signatures. So signatures that are definitely correlated in time. And on this plot, the scales vary a lot for pulsar to pulsar. So even though you see this red noise signature, this is only going from +5 to -5 microseconds, whereas some of these other ones that look white go from -50 to 50, right? So there's a lot of variety in both like the RMS we can achieve, depending on the particular pulsar, and the kind of noise we might see that's intrinsic to that pulsar, right? So we don't think these red noise signatures are gravitational waves because we only are seeing things like that in a couple of the pulsars. Those are intrinsic to those pulsars. So what do we expect gravitational waves to look like in pulsar timing residuals? So let's start with this left plot here. So this top left plot shows what the signature of a stochastic background would be in pulsar timing residuals before we do a fit for any timing model. So we expect the stochastic background to be stronger at lower frequencies. And by the way, this isn't true just for supermassive black hole binaries. It's true for any of these backgrounds that you've heard of, like cosmic strings, primordial gravitational waves. They all have more power at the lower frequencies. So we would expect this very long, like time constant variation in the pulsar residuals. However, when we fit the pulsar timing model out, much of this is going to get absorbed into the pulsar timing parameters, right? We don't know it's there, and we don't know its shape in any one pulsar. So we have no choice but to absorb this into the pulsar timing parameters. And so after fitting the pulsar timing model, then it's going to look something like that in our pulsar timing residuals. These different colors are just like 3 different random pulsars in different directions of the sky. And they're just illustrate that this will look different in different pulsars. On the right shows the residuals that we expect for a single gravitational wave source. And so you can see pulsars in different directions will have different responses to that gravitational wave source. They'll have different amplitudes and different phases. Of course, the period will be the same for all the different pulsars though, right? And that's determined by the orbit of the supermassive black hole binary. And unless you're very unlucky and your gravitational wave source has a period of a year or the same period as a binary orbit or something like that that you're fitting for in the data, this signature is going to remain preserved in the data and not be absorbed by the timing model. So in the final residuals after the timing model fit, you'll still see this same signature there. Okay. This is what we are looking for in our pulsar timing data, these kinds of signatures. I'm not going to talk a lot about this at all. Golem went through a lot of this in his talk. There might be a few of you who weren't there. So I'll just go through this really briefly, but I'm not going to just kind of do a deep dive into any of these. But the point is that, you know, our experiment is messy. We're not LIGO, right? We can't actually go to a detector and like, you know, improve our laser power or calibrate the noise in any kind of experimental way. We just have to take what we've got. We can't control the pulsars, and there are intrinsic and extrinsic sources of noise that we just have to live with, right? So pulsars aren't perfect rotators. They have some rotational irregularities, some what we call like intrinsic spin noise. Pulses jitter. The phases of the single pulses kind of jump back and forth in phase. They have different amplitudes. These both add noise to the data. They're also extrinsic sources of noise. One, due to the interstellar medium, so dispersion measure variations, scattering variations in the ISM. We need to correct the times of arrival of our pulses to the solar system barycenter to remove the movement of the Earth around the sun and all the little gravitational hubs of the planets in the solar system. So we need concrete ephemeris. If that's not right, that would be a source of our errors with our plots, right? It's going to be an error or offset from some perfect time standard. Saying no is that we can model all these different sources of noise because they all have different signatures, right? So the ISM stuff is chromatic. That means that it depends on radio frequencies. That's a very special signature. We can use to tease that stuff out with other sources of noise. Pulse jitter is not correlated in time. We can use that to tease out that contribution, right? It's just white noise, completely uncorrelated from one observation to the next. The spin noise will be correlated in time, but not correlated in space. This ephemeris noise will be correlated in space, but it won't be quadrupolar like the gravitational wave background, right? So the gravitational wave background is the only source of noise in the data that's achromatic, correlated in time, correlated in space, and has this very special quadrupolar signature. These equations at the bottom are just meant to remind you all that like we do these noise analyses in the frequency domain. So we're basically, you know, taking spectra of all these residuals and then fitting different spectral components to that data. Okay, so I'm going to now talk about our results. I'm going to start with our like penultimate data set, the one before our current one, just to kind of lead you through a little bit of the story up until the current time. So our 11-year data set was released back in 2018. And that data set was a really interesting story because we do this experiment of looking for common noise in the data, right? So we take spectra, for all the pulsar timing residuals, and we see if there's a common source of noise. And that means a common contribution to their spectra that has the same amplitude and the same spectral index in all of the pulsars in the array. And then we calculate a PDF of that common noise versus like gravitational wave background, right? So we want to convert the power in that common noise to a gravitational wave background. When we first did this experiment for our 11-year data set with 37 pulsars, we got this line here, right? And so this was really exciting. This looked like a detection of a strong common noise process. It peaked like at a particular gravitational wave amplitude. That was really cool. We started buying champagne, and this is great. We have this like really exciting detection. And then we said, well, wait a minute, let's see if like we can make it go away, right? Like before we get all excited that we've detected this common process, can we make it go away? And indeed we could. And what we did is we replaced this ephemeris, right? These DE things are all ephemerides, planetary ephemeris from the Jet Propulsion Laboratory with a different ephemeris. And depending on what ephemeris we use, we got like a very different answer. So that was bad. And what we realized was that, the ephemeris was not accurate enough for our purposes. It just wasn't accurate enough. And so what it was doing was leaving behind a source of common noise in all of our pulsars because of this incorrect ephemeris. So we developed a new code. It's called BaseFM. Some of you are familiar with it if you're doing pulsar timing work. And BaseFM will allow us to start with any of these ephemerides. And then it tweaks the ephemeris to remove any dipolar correlation due to a bad ephemeris to arrive at a new, better solution for the ephemeris. And with this code, regardless of which ephemeris we start with, we end up with what looks like an upper limit, right? So these correct PDFs are all upper limits. So that was a little disappointing, but it was still exciting because this upper limit was very sensitive. And it was so sensitive that we could actually set some interesting astrophysical constraints from this 11-year data set, right? So there's all these different predictions for black hole mass versus galactic bulge mass. They look like this. These are measured points, these black points, and these different colored lines are different predictions from different papers. And some of them predict bigger black hole masses, some of them predict smaller black hole masses. And using our limit, we could actually say that these papers, this Cormedy and Ho and McConnell and Ma papers are disfavored. Because if they were right, we should have made a detection. If black holes were that massive, we should have seen them in our data set, right? So this was a pretty sensitive limit that allowed us to do like real astrophysics. We could rule out parameter space. So that was really fun. Okay, so we went into the next data set, which is the 12.5-year data set. So this is another 1.5 years of data and another 2 pulsars. We went into this next data set thinking we were going to set a slightly better limit and we'd be able to do like even more fun astrophysics, but that wasn't the case. We detected a very strong common noise process in the data. So this is a similar plot here to what you saw before. So this is like probability density versus gravitational wave amplitude. Really strong peak at a particular gravitational wave amplitude. And we get that whether we use a fixed solar system ephemeris or whether we use our BaseFM code marginalizes over the ephemeris. You might wonder how to use a fixed one now, and that's because the ephemeris have improved, of course. So this new JPL ephemeris and this French INPA ephemeris are much better. Largely due to Juno, which is a satellite that's made its way to Jupiter and has measured the mass of Jupiter really, really accurately. So we don't even need our BaseFM code anymore. The ephemerides are now good enough. So this is very exciting. There's very strong evidence for this common process. The Bayes factor is about 10,000 for the common process over independent red noise processes in all the individual pulsars. So this is very significant evidence that there is indeed a common spectral process and not just individual pulsar noise, right? We can say with a pretty high degree of certainty that there's some common process. In this data set, however, we do not see quadrupolar correlations. This shows the correlated power versus pulsar angular separation. The black points are our data, and this blue dotted line is our fit. This is just, these points are binned, right, somewhat arbitrarily. So we can't show every single pair on this plot. So we don't actually fit these indeed points. This is just like an illustration, but you can clearly see that they are not really hugging this Hellings and Downs curve, right? So this is the best fit to the data, but there's no evidence for these quadrupolar correlations. There's also no evidence in the 12.5 year for monopolar or dipolar correlations. There's no evidence for any angular correlations. We just see this common noise process. That's it. One thing I just wanted to mention, this is, I think Kai talked about how our limit, our measurement is kind of like challenging models, right? That it's much larger than you'd expect for supermassive black hole binary models. And it is larger. One thing that you'll notice if you look carefully is that we have a lot of probability in this PDF above previously reported limits. So here we are, this is minus 14.5, and this has gone to like basically 0. On our detection, there's still a fair bit of probability in this regime where that upper limit, that PDF has fallen off pretty dramatically, and that's true. Our amplitude is higher than the previous upper limit, and we attribute this to better modeling of intrinsic red noise in the pulsars. So this is okay; it's nothing to really worry about. But it actually means that some of those models, which we said were disfavored in the 11 year, like this Kormendy and Ho model here, might actually be correct. These large black hole masses are actually consistent with this detection of the common red noise. Okay, so let's look a little bit in more detail at this common red noise process. The first thing we want to know, right, there's some common process. Is it real, right? Is this like a real thing? Or is this just like a blip, right? Do we just have this accidental process? So some of the things we've done to show that, one of the things we've done are phase shifts. So just shifting the phases of all the signals. Another thing we've done are sky scrambles. So just taking the pulsars and moving them around, right? So keeping the data exactly the same, but just swapping the positions of all the pulsars. We do this a whole bunch of times and just see how many times when we do these phase shifts or sky scrambles, which basically randomize the data set, how many times do we detect something as significant as this, right? As this common red noise process. And these show the results of that. So here's the measured signal to noise in the common process, this thing here. And these are the results of these sky scrambles and phase shifts. And you can see that about 8 or 9% of the time we get something with similar significance. This is like, okay, I mean, it shows it's probably real, but this isn't, we don't have a smart percentage, right, for this to be super significant, but correlation yet to, right? See a little bit more significant. The thing we can do, of course, is look at the actual spectrum, the noise sets, and this left plot here shows spectrum. So this is a common process of wave versus gravitational wave frequency. And these gray bands here, you can see it's very red. There's a lot of power at low frequencies. We can fit different kinds of power laws to the frequencies. The best one is this orange one, which fits the 5 lowest frequencies, or this broken power law. This green one is not a good fit because it kind of is dominated by all this high frequency white noise, which isn't the real gravitational wave signature. If we look at these orange or blue fits, we get spectral indices between 4 and 5 and an amplitude of about minus 15 something. This is really nice. So this is consistent with what we expect for supermassive black hole binaries. We expect 13/3 for supermassive black hole binaries. That's here. So it's just about consistent with it. It's also consistent with what we expect for cosmic strings. We saw that in Kai's talk yesterday. There's a very wide range of spectral indices, all of them, well, not all of them, but some of them consistent with this. It's also consistent with primordial gravitational waves. So we can't say what this is at all. We can only speculate, but at least it's consistent with multiple things, right? There is an astrophysical explanation. I just checked today, there's now 522 citations for this paper. Most of them I do not understand. Most of these papers are people suggesting, completely, I don't want to say crazy. I mean, these are all viable things, but lots of exotic physics explanations. People got really excited over this common process. And there's some more explanations than we have frequency bins in our spectrum. More explanations than pulsars, I think, in our array. So of course, as most of you know, the same process is seen in the EPTA, the PPTA, and the IPTA data, all with consistent amplitude and spectral index. This is the PPTA plot, the EPTA plot, and this is the combined IPTA DR2 plots. This is from the second data release. You can see this is completely consistent. This table is taken from that IPTA data release paper. You can see in the IPTA data, the Hellings and Downs correlations are preferred over a common process with no angular correlations, but just a little bit, Bayes factor of a few, so that's not really significant. But the common process is really dramatically preferred over intrinsic pulsar noise, and the common process is also preferred over a monopolar or dipolar signature. So that's really good news, right? So no quadrupolar correlations yet. We cannot say this is gravitational waves, but everything is aligning with expectations for the early stages of a gravitational wave detection. So when are we actually going to see the gravitational waves? So we've done simulations, sort of like extrapolating our data set out. And if we do that out to 20 years, we see that in our 15-year slice of data, we should be detecting angular correlations at something like a signal to noise of 4 to 7. And we'll be publishing this data set very soon. This is not real data. This is a simulated Hellings and Downs curve. What we would expect in our 15-year data set, we should see correlations that look something like this. So they should be visible by eye if what was in the 12.5-year data set is indeed a gravitational wave signal. We should see correlations in the data set. We won't be able to say anything about the source. We'll be able to constrain both the amplitude and the spectrum to something like 40%. Not very good. So we're not going to be able to say a supermassive black hole binaries, cosmic strings, whatever. There'll probably be a million more citations to that 15-year paper with a host of other explanations. We won't be able to say anything about the source. And of course, the signal to noise will be much higher in combined international pulsar timing array data. And I'd much rather show an IPTA projection here, but we just haven't done that work yet. So this is just the nanograph projection. A little bit about the next step. So like, if there is this signature in the 15-year, if we indeed see these angular correlations, what do we want to do next? Well, we want to figure out the source, right? So what is the source of this? Is it supermassive black hole binaries? Is it cosmic strings? It's some combination. One really important thing that we want to be able to do going forward is disentangle multiple background contributions, because it's likely that there's not just one background contribution, right? It's certain there's not just one. We know that primordial gravitational waves should exist, maybe at a very low level, but they're there. Andrew Kaiser, Andrew is a grad student working with me. He recently published a paper where we look at like when will we be able to disentangle multiple contributions. This shows amplitude versus timing baseline, again, out to 20 years. This is the fractional uncertainty on a spectral index for different backgrounds. This is a little bit of a complicated plot to go through quickly, but basically, if we have an amplitude about half of what we detected in the 12.5-year and a spectral index of -5, that's what we expect for primordial gravitational waves. At about the 20-year mark, we'd be able to distinguish that second background if the amplitude's about half the primary background level. So about 5 more years, we'll be able to say whether there are 2 backgrounds. Sooner if they're more comparable in strength. And this just shows the Bayes factor versus time for this second background. And you can see that at about 20 years, we're getting Bayes factors almost of 100, right? So about 20 years will be a good time frame to do that. Another thing that'll be really important for determining the source of the background is anisotropy. We expect the supermassive black hole binary background to be a little bit anisotropic. We won't have like perfectly isotropic supermassive black hole binaries, right? But we would expect cosmological backgrounds like cosmic strings, primordial gravitational waves, they should be more anisotropic. So this shows that at about the 20-year slice, this is a recent paper by Nihan Pol et al. We should be able to detect anisotropy. So these are the isotropic signal to noise, total signal to noise, and the signal to noise fitting for the anisotropic part of the signal. This assumes a 30% level anisotropy at about a signal to noise of 3, right? And you can read this paper. There's lots more details I don't have time to go into, but within 5 years, we should be able to say something about the anisotropy of the signal, and that'll be pretty exciting. And I'm sorry I'm going a little over, but hopefully it's okay since we had all the issues. So that's the stochastic background stuff. Of course, we're also searching for single sources in our data. We just submitted our 12.5-year continuous wave results. This is not yet accepted by AppJ, but we just popped it on the archive. So you can look at it. Obviously, we haven't detected any single sources, but we've searched for single sources in multiple directions of the galaxy. And we kind of do two things with the single source results. The one thing we can quote as a sky average limit. We can also look at the limit in the most sensitive sky location. They're quite different, more than a factor of 2. That's because our pulsars are distributed very non-isotropically, right? So this is an ATOP plot of the galaxy. The stars are our pulsars. The red ones are new ones that were added to this analysis that we didn't have in the last analysis. So you can see we have a lot of sensitivity in this part of the galaxy and very little sensitivity in this part of the galaxy, just because of the distribution of our pulsars. We have a lot of pulsars over here and not very many over here. This part of the sky, of course, we can't see. This is in the southern hemisphere, but some parts of the sky are visible, but we just need to find more pulsars. So you can see we can go out to about 80 megaparsecs or so for a billion solar mass binary. So in this direction of the sky, we can say there are no billion solar mass binaries at our most sensitive frequency out to about 80 megaparsec. This shows the sky average limits as a function of frequency. And you can see the 5-year, the 9-year, the 11-year. You might wonder what is going on? Why is the 12.5-year not doing much better than the 11-year? The reason for that is that now we have this common red noise process in the data, which really affects our sensitivity to the single sources. So this is because of this common red noise process. Up here at high frequencies, the limit is actually pretty dramatically improved. If you look, you can see the blue lines up here, the red lines down there. It's about a factor of 1.4. Around our most sensitive frequency, though, there's almost no improvement due to this common red noise process. So this is something we're going to need to really have to worry about in single source searches. Is how do we fit for this common process at the same time? So the limits are consistent with supermassive black hole binary populations. So people talk about like a supermassive black hole binary mass function, which basically describes the number of supermassive black hole binaries as a function of mass, as a function of redshift, and as a function of frequency. And you can see the power, the gravitational wave power, or squared strain. You'd integrate over the chirp mass, the redshift, to come up with that power. So this shows our constraints. This is the all sky limit. This is the best limit. And this is the like part of parameter space that this is rolled out. And basically, this mass is kind of like the maximum end of that black hole mass function. This is a billion solar masses right here. So there's still a lot of parameter space that remains even with this continuous wave limit. Another way to say this is that we really shouldn't have detected a single source in this data, given our current understanding of supermassive black hole binary mass functions. Basically, we should have detected 10 to the minus 4 to 10 to the minus 3 sources in this data set, and we didn't see any. So this is all perfectly consistent. So this isn't really, we're not really constraining this mass function, but it's nice to see that it's consistent. One thing we can do with this data set, and we've done with other data sets, is look for like individual supermassive black hole binary sources. So there's this very famous galaxy called 3C66b, which is purported to have a supermassive black hole binary at its core. It's really massive. It's like a billion solar masses. It has an orbital period of about a year. It's pretty nearby. So in this 12.5-year continuous wave paper, we searched for this particular galaxy using the priors on its parameters from electromagnetic observations. And this is, these are our upper limits, these purple and red lines. One of them is assuming we have a common process, so fixing the common process in our data. This one is not. We get a slightly worse limit when we kind of like model the common red noise. This is our 11-year limit. So you can see we've done a lot better from 11-year to 12.5-year for this particular binary. This is because it's periods a year. So it's really far from our most sensitive frequency. So this is very exciting. This dotted line is the center of the electromagnetic predicted region for the mass, and this orange band is the electromagnetic prediction. So we're really close to starting to dip into this orange region where we might actually expect to make a detection of this supermassive black hole binary. So that's like really, really exciting. We expect to see this thing, in a few years, or rule out the current predicted limit. The other thing I just want to mention about this, and I'm almost done, because we were talking about like distances and VLBI yesterday, is that one thing that we've done new in this paper is kind of have like we have a new approach to pulsar distances, even though we don't know the distances well enough to really fix those pulsar terms in the model, right? We don't know the distances well enough to do that. We do marginalize over all the pulsar distances. And to do that, we basically look at each pulsar in the data set, and we just use the best distance, whatever it might be for that pulsar. So for some of them, that's a parallax distance measured through pulsar timing. For some of them, it's a parallax distance measured through VLBI, not through pulsar timing. And for some of them, it's just a distance from a dispersion measure and a DM model. So for each pulsar, we have a distance. This is the full width at half max of a Gaussian prior for each of those pulsars. And so this doesn't actually make a big difference to the results at this point because they're so big, but it's, I think, a more elegant way of doing it than what we did before. In our last data set, we just assumed a 1 kiloparsec distance for all the pulsars, which wasn't very well informed. Okay, so my last point, I just have a couple more slides just to talk about like what the goals are going forward for Nanograv and also for the IPTA, of course. So I think one really important goal for the next 5 to 10 years of PTA science is growing the number of millisecond pulsars. So we would kind of like to get to something like 200 MSPs by 2030. The reason for that is that you can look at the signal to noise in these Hellings and Downs correlations versus the number of pulsars. These sigmas are the cross correlation uncertainties. So basically, these are brighter signals, cleaner data, weaker signals, less good data. And you can see that in the high signal to noise regime, which we think we're in, this grows linearly with the number of pulsars. So the signal to noise is going to grow linearly with the number of pulsars. So the more pulsars we can add, the better we can do. This shows the signal to noise versus this uncertainty. And you can see that's proportional to 1 over this uncertainty. So it also decreases linearly with this as this uncertainty grows. And just so you can get an idea of what this uncertainty means, you can kind of like approximate it in either a weak gravitational wave regime or a strong gravitational wave regime. In the weak regime, it goes like this is the weighted RMS of the data. So the precision of your data squared, time span to some factor, cadence. In the strong regime, it goes like the amplitude of the gravitational wave signal over this factor of the cadence and time. And we're kind of like in between. I don't have much time to talk about this, but this cross-correlation uncertainty will be better for lower RMSs, longer time spans, higher cadences, right? Okay, so we want to grow the array. A big thing for Nanograv is commissioning the GBT's wideband receiver. So we now have a wideband receiver on the Green Bank telescope that covers all the way from like 700 megahertz to 4 gigahertz, which is really fantastic. It's way more bandwidth than we currently have. We currently have only 200 megahertz down here and then about 800 megahertz in here. This will be really great and it'll increase our efficiency. We'll no longer need to observe at 2 separate frequencies for all of our pulsars. We can just observe with 1. We're also in the process of incorporating CHIME data into our data set. So CHIME is a transit telescope, so it observes pulsars every single day. And this daily cadence is really complementary to the GBT. This is a plot for a paper by Emmanuel Fonseca on 0740, the high mass pulsar. This is about a year of data, actually 58550, a little more, almost 2 years of data, where we could, oh, I can't do my math. This is a year of data. So you can see the green and blue points are Green Bank data and the yellow points are CHIME data. And you can just see like how much more rapidly CHIME samples this pulsar than the GBT, right? There's a lot more yellow points, so it's getting much higher cadence sampling. This shows the DM measurements with the GBT and CHIME, and oh my gosh, just look at like how much better CHIME is determining the DM. And it's just because it's got that 400 to 800 megahertz bandwidth, a much lower frequency wideband. It's so much better than the GBT at these DM measurements. So I think it's going to make a really huge improvement in our data, in particular the DM, and also scattering modeling. And this is a whole other talk. We don't have much time to go into it. Finally, we really need to build a replacement for Arecibo, both for Nanograv and the IPTA in general. Arecibo was a big part of the IPTA data sets. One telescope we're really pushing is this DSA 2000 telescope. It'll be 2,000 small dishes like this, probably in Nevada. Why do we need it? Well, we might detect the stochastic background with our current setup, but if we want to start detecting single sources and really like mapping the low frequency gravitational wave universe, we need a lot more sensitivity. So this plot shows strain versus frequency again. This gray band are the predicted strains of a population of supermassive black hole binaries. This green curve is what we get if we just keep doing what we're doing. We extend the current observations. This blue band is what we get if we add DSA 2000. So having that additional collecting area will allow us to detect many, many, many more supermassive black hole binaries. It'll be really, really, really important. Characterize the stochastic background better, of course, as well. We're hoping to get about a quarter of the time on this telescope. Okay. Detect single sources. So obviously we want to get into the regime where we're detecting many single sources. There was a recent paper by Ben Spency, Neil Cornish, and Luke Kelly, which predicts that the 15-year data set has a 6% chance of a single source detection. I think that's a little optimistic. It was very there's a lot of kind of optimistic assumptions in the paper, but it gives you an idea that we're not that far off, right? This is assuming a reasonable population from the illustrious simulation of black hole binaries. This plot here is also based on the illustrious simulation. These are predicted strains and frequencies of a population of supermassive black hole binaries. And these are IPTA sensitivity curves in 2025, 2030, 2035. They're getting better with time. That's great. And you can see that in 2025, the IPTA could access several supermassive black hole binaries. And this is 3C66b. It should, without a doubt, see 3C66b at its current predicted gravitational wave strain. So this is really, really exciting, and I hope a huge motivation for us to finish IPTA DR3. So this is going to include the 15-year, the EPTA, PPTA, and of course the first Indian PTA data release. Hopefully the Meerkat data release. That's the only one that's not, I don't think it's been completely added yet. And that group is also, they're putting together an early release right now for only 15 pulsars, but the best ones. And so this will be really exciting. These will be based on the papers that are currently being written on the current results, which we're calling the 3P plus papers. So this data set here should have a weak detection of gravitational wave signal, but the full analysis will include all of this data. And of course, the Indian PTA data will be really important at those low frequencies for helping constrain dispersion measures. And in the future, I'd really like to see us have, like, instead of data releases, just continuous integration, right? All the pulsar timing arrays, we just continuously integrate our data into a constantly updated data set that just is living and updated. This is not meant for anyone to actually read through in any kind of detail, but we have funding from the National Science Foundation from this ExcelNet program for a full-time project manager and cyber infrastructure person. And these are all the steps we've identified along the way to get to the point where we have this like continuous and automated data set, which would be totally amazing. I'm putting this up just because it's a really pretty picture. But of course, the goal of all of this is multi-messenger astrophysics. We want to get to the point where we're characterizing supermassive black hole binaries, both with our pulsar timing array, with telescopes on Earth, with telescopes in the sky, and with every kind of messenger, from gravitational waves to photons to neutrinos, right? So this is the image that we're going for, and telescopes all around the world, right? So I really enjoyed coming and talking to all of you and like being here on this trip, because I think like this is the goal. We all want to work together to build this huge worldwide gravitational wave observatory. And I will just leave this up. There's nothing really new here I need to say.
So let's thank Maura again for a very fantastic and awesome talk. So I open the floor to questions. So maybe we'll start with non-experts or people who don't work in pulsar timing first. Yeah, please.
Hello, thanks for the very nice talk. So I just wanted, I'm not in this field, so it may be a naive question for you, but you mentioned that all these signals can point out to various sources like cosmic strings or the stochastic, all these backgrounds. But what precision do we need to actually distinguish between these different kind of sources giving these signals?
Yeah, so they all look kind of similar. So a background due to cosmic strings or a background due to primordial gravitational waves. And there's different primordial sources. There are primordial black holes. There's also like early universe inflation. There's all these predictions. They all have red spectra. So they all have similar spectral indices between like -3 and -5, something like that. And similar-ish amplitudes. So this first data set, we won't be able to tell it all. We'll just see this noise process and that's it. And then what we want to do is really characterize that spectrum very, very well. Some of the models predict not a straight power law, so a spectrum that will like fall off or roll over on either side. And we also might detect a broken power law, which is the intersection of two different spectra. And we think we'll be able to do that, in something like 5 years. The other tool we have is this anisotropy. The other backgrounds, these cosmological backgrounds, should be isotropic, it may be like very small deviations, but the supermassive black hole binary one will not be, it'll have some anisotropy. So those are the kind of tricks that we're playing. I personally think, the background will be dominated by the supermassive black hole binary. It's just because that's kind of a sure thing. like we know they're out there. We have a lot of observational evidence, whereas the cosmic strings and the other ones are a little more speculative. Although I would take them. That would also be a huge, exciting result if we detected a background from some of those.
Thanks. Because if some of these signals can distinguish between these scenarios, then of course there are many other early universe phenomena which are not known.
For sure. Yeah. I mean, it may be, a decade before we can really say with certainty what we're seeing in that stochastic background. So it'll give theorists a lot of fodder for papers. One other thing I'll mention is that once LISA is launched, right, which filled that like middle range of phase space, and that'll also be a really nice check. Like if someone claims that there are primordial gravitational waves in our data set, well, that spectrum should extend into the LISA range. And so that'll provide another good check on interpretation.
Thank you.
Okay, my understanding is there are no questions on Zoom, but I'll just still ask one more. Okay, so then questions from others in the audience. So let me start with the students. Yeah, Jaikumba, just wait till the mic is passed around.
Yeah, Maura, I had a question on the HD correlation. So there you said for some of them, the binning is arbitrary, right? So how sensitive is it to the binning? Like, I mean, how do we take care of the binning? What is the bins? How do we decide that?
Yeah, so we don't bin the data at all for the actual detection statistics or analysis. We take like each pairwise correlation. So each of the 70 pulsars, we cross correlate with each of the other 69 pulsars. So the statistics we quote are not at all sensitive to binning because we don't bin them. This is just for like visualization. And in fact, I think for the, if we have a signature in say the 15-year data set, I think it'd be really important to just provide the data so people can bin it however they want. Because I think you can, by playing with this simulated data, you can bin it, you can pick contrived bins so that it looks really great and lines up perfectly, or you can pick ways of binning it that like wash out the correlation, right? So this is very much just like a visual, just to visualize it.
Okay, so the model will be fitted with the with all the correlation, with all the angular separations.
Yeah, no binning in the actual analysis. It's just like, but to show it by eye, you got to bin because we can't show how many 70 times 69 points would be unreasonable.
I'm also a little bit confused about the early data release, which we are planning for. Actually, 20 pulsars we have listed actually. So I mean, is there a motivation to search there also in that data for just 20 pulsars?
Oh, so this is wrong. It's 20, not 15.
Yeah. So
okay.
we have a list of 20. So
yeah. No, actually, that's a really good question. I think so. I'm not I think you know more about this than I do because you're working.
I'm still wondering about the motivation for it because
From my perspective, like we want to develop tools. So it'd be really useful
okay,
to
okay,
run the detection analysis software on this data release before getting to the full thing and then realizing, that enterprise can't handle some aspect. I guess there's no downside. I was going to say the only downside is maybe something will be seen in this, and then maybe that'll demotivate people from doing the full data release, but I don't think so. I think it would be the opposite. I think it would motivate people to get the full thing done because it would be an even better detection in that.
Yeah, and finally, I have a question. When we do this IPTA combination, maybe it was discussed some time back, but what are we going to do about the various DM measurements which different PTAs have different PTAs have different ways of measuring the DMs, right? PTA does DM1, DM2, and nanograph does DMXs. We are also doing DMXs. So, is there a final decision on in future? What are we going to use?
I do not know. There's been lots and lots of.
I was not part of the early discussions on this. So,
I think we're moving away from DMX and going towards either DM derivatives or Gaussian processes, which I think are maybe a more natural way because there's just so many measurements. The DMX gets to be really messy if you have, lots of data points within a window. So I think we're going to move towards like Gaussian processes. But yeah, I don't want to say the wrong thing because I've not been working on this combined data set myself.
I think this is a topic for a busy week and things.
Yeah, thanks.
Any other questions? Okay. Prerna? Oh, okay, fine.
You said the common process is reducing the effect of 12.5 year compared to the 11 years.
Yeah.
Why is that?
You mean that when we do the single source search?
Yeah.
Because we have this strong noise process in the data. And so because we have this strong noise process that just decreases our sensitivity to single sources, it's just like kind of any noise process. We can model it. We can't remove it like it's there, but we do fit for it. So we fit for that common process in addition to single continuous wave sources. So we do like, we know its amplitude and spectrum. And so we do fit for it, but it's still noisy. So it's not, it's not like a deterministic thing that we can remove and recover all the sensitivity. Yeah, it's a good question.
You were talking about the wideband receiver for GBT coming. So what would be the bandwidth of observation?
So the whole receiver goes from like 0.7 to 4 gigahertz. I don't think we're going to use that whole band because you can't time any millisecond pulsars really above 3 gigahertz. So we'll probably go from like 0.7 to 3. But I think it'll probably be decided. We haven't started this yet, and the GBT is now down for a bit. So it'll probably be decided on a pulsar by pulsar basis, right? So it might only make sense to go to 2 if they have a really steep spectrum. Some it might make sense to go all the way to 3. But it's still a little TBD. We haven't observed any of our pulsars with it yet, not one. Like it's still in the really early stages of commissioning.
Okay, so let me take the chair's prerogative. So again, just thinking beyond. So do you have any comments on this recent paper by the UC Santa Cruz group? I think William DeRosa and Jeff Doru who talked about searching for sub-nanohertz gravitational waves using pulsar parameter drifts. Is that a promising method or not very sanguine about it?
I read the paper. I don't think it's crazy though. We do expect, like if there are gravitational waves, they'll get absorbed into pulsar timing parameters.
If that works out, that would be again very promising, which can break the degeneracies. I think coming back to our question.
It's an interesting idea. I wrote a paper with an undergrad at WVU a long time ago about looking for discrepancies between DLBI parallaxes and proper motions and timing parallaxes and proper motions. And one of the explanations could be that the timing ones are absorbing gravitational waves. And so we use that to set a limit on the gravitational wave background. It was really high and just it went over a year, but I think it's the same idea.
Okay.
Right? Yeah. I think it's a cool idea.
Okay. Any other questions? Yeah, Pratik.
If I understood correctly, in one of your slides, you mentioned that modeling the common red noise process does not lead to a improved mass estimate for one of the binary supermassive black hole candidates. So why is it so? I mean, after modeling for the common red noise.
So you're talking about this one here.
Yes.
Yeah, well, I think it's because we're fitting for more stuff. So we're fitting both for the single source, and then we're also fitting for the common red noise process as well. Like we're not fixing it. We allow that to vary too. And so it's just, I think the more parameters you have, the less sensitive, your limit is. We just have more free parameters. I think that's the explanation.
So does it imply that with better, maybe common red noise modeling, we will have a better estimate of the mass? Is it so?
Yeah, I think that is accurate. Yeah. Okay. Yeah. And there's not a huge difference, but yeah, it is a little bit worse.
Thanks.
Goku.
Amazing talk as usual, Mara. And I've been listening to your many talks. I'm really enjoying all of them. So again, I will start from here. Imagine you, instead of modeling, these searches actually incorporated, as you mentioned, the pulsar distances, varying them, So can you get better kind of constraints if you assume them not in circular orbit, but with some eccentricity, in the sense of, the advanced superastron sort of walks in there, even though eccentricity need not be high. This is, Belinda was kind of thinking, trying to do that. So this is something we may want to.
Definitely, yeah. Like our searches now are all assuming circular orbits, just circular orbits. And I think it's not, as you know, it's not hard to model the waveforms for the eccentricity. It's not like LIGO, they're simple. It's just computationally really a challenge to search over that wide range of eccentricities. No,
we can even constrain tiny eccentricity and see whether that helps them. And so
yeah, it's definitely worth doing. I think, there may only be a handful of these binaries that are detectable over the next 5 to 10 years. And what if one of them is in an eccentric orbit? We wouldn't want to miss it. And we also can do, we can also set constraints from the stochastic background too. Like once we detect that with enough significance, we can actually set constraints on eccentricities just based on the level of that. So maybe that'll help inform how important it is to model.
But that will require you to see the turnover, right?
Yes.
And that's a bit complicated. It will take time. So.
So I think actually BCJ has a question on Zoom. So I don't know where the mic is. So maybe just put the mic near the Zoom. So BCJ, if you can hear me, you can ask. Sorry?
Yeah, I can hear you. Can you hear me? Can you hear me?
Yes.
Am I audible?
Yes.
Okay. Yeah. Hi, Mora. Excellent talk and very nice sort of overview of where we are. And it was great to have you here in India. Sorry, I have not been able to be present in person. It's sort of the thing where Gopu left. So about the parallax distances. So if you recollect, Harvey Siemens had written a paper in 2013 about scaling loss. And he mentioned that once we transit into the strong gravitational wave signal regime, the signal to noise ratio scaling would actually, the slope of increase of signal to noise ratio will decline. And that would decline basically because in addition to the usual noise processes, we will also have a gravitational wave noise, which is primarily coming from the pulsar term, okay, which we have been ignoring. In the correlations, we ignore the pulsar term. But once we actually have detected, say, 5 sigma, 6 sigma, 7 sigma detection, the pulsar terms will become important. And then the distances will become important. So I was wondering, has anyone thought from nanograv on what to do about these undetermined terms, and whether a large VLBI program would be a very useful thing going forwards for the next decade of PTA? Would a large VLBI program coordinating between several telescopes around the world be a very useful tool to sort of work in the strong signal regime? So I just wanted to know, what are your thoughts on that?
Yeah, I mean, I think it's probably unfeasible to get, large VLBA programs for all of the MSPs. But I mean, I think if we picked the few very brightest ones and even just got really good distances for them, that would really help. Like, even if we could just include some of the pulsar terms, we don't need all of them. I think it'd be worthwhile. We have to do the calculations, right? Like, which ones could we, to make it useful, you need to get the distance to within a gravitational wave wavelength. And so there's probably not too many we can do that for, but probably a few within a few years. I don't know. We'd have to work it out. I think it's definitely worthwhile, though. I think it's kind of been on the back burner. We've been so focused on the stochastic background, but for single source searches, it'd be really great if we could include some of the pulsar terms. You're absolutely right. Let's talk about it.
Yes, so I guess that's something going forwards we should all discuss amongst the PTA community.
Definitely.
And how to get the resources for that. You're right that to coordinate between large telescopes to do this is going to be a nightmare. But certainly we should try. And as an IPTA thing, we can actually push for some of these things and get time. So
Adam Deller is talking tomorrow, right? Tomorrow morning. So we'll hear about this tomorrow morning. So maybe we can.
Adam is going to talk about this. So in fact, one of the reasons for him being here is precisely to throw some light on what he's been doing. And so it would be great to discuss this, certainly.
Yeah, let's talk about it.
So I think Gopu had one more question.
Yes, I mean, so this is what we were kind of chatting about, a possible telescopes, VLBA using GMRT, Chiang Mai, and then maybe something, in Japan will be perfect. It can kind of match VLBA, but big dishes, so that hopefully, like 40-meter GMRT and something even smaller will be amazing. So,
yeah, and you can see, we're really not close to where we need to be.
That's right.
Except for, there's a couple of them. Like, we really want to get to this, oh my God, like the 0.0, we want to get like to 0.001.
Yes, 7840.
Really, like parsec level errors. That's about our gravitational wave wavelength. So none of these pulsars are that close. 0030 and 1740 are within a factor of 10, but factor of 10 is still pretty not good. Yeah. We have a lot of work to do.
Yeah, I have just a follow-up question, and this is about you mentioned this about the Juno allowing us better ephemeris, and because of that, you have the I think it's 438 or something, 36 or 36. I can't remember which one of those numbers. But then you have the base FM, but that was it showed, because you kind of marginalizing, but then the amplitude sort of shifted to the left or something like that, right? Do we have an explanation for that?
I think that we're absorbing a little bit of the gravitational wave signature when we fit for the correlations due to the ephemeris.
Yeah, this is the
I
one.
think it's like broadening and shifting to the left because we're just absorbing some of that gravitational wave power when we fit for the ephemeris errors.
That makes sense.
Yeah.
Thank you.
Okay, any questions? Any more questions from BCJ since it's online? Okay, so if not, so further questions, I think we can discuss over dinner in the next few days. So let's thank Maura again for a very stimulating talk, given us plenty of food for thought over the next few years. Thank you, Maura. Also, thank you for taking all the questions. I think
let me get you the mic